In this episode of our 6502 build, we're going to look at the 6502 startup sequence, what it does, and how long it takes, and the pitfalls. Roll the titles.
Is that it?
In episode 3 of this series, we left off with this simple setup of our 6502 with its clock inputs being pulsed by the controller of this Arduino, which in itself only changes the clock when a button was pressed, this one in fact. You may ask why use an Arduino? Why not just connect the button directly to the processor? And well, we could do that, but something called switch binds would make a right pig's ear of the clock signal, causing multiple pulses on just one single press of the button. Using the Arduino allows us to clean up the button press and just send a single low or high pulse out to the clock. Let's have a look at the code, which is available on the project page listed in the description below. We have some constants at the start, the output clock signal, which goes to the 6502, is Arduino's pin 3. The button press is on a 0, and the remaining 3 are all to do with debouncing that switch. Note that we don't need anything as complex as a full Arduino to debounce a switch. Other methods are available, but as we will be using Arduinos to help us debug our 6502 system, it seems sensible to introduce one now to do this job. We set our pins here in the setup. Note that the button is pulled high by default. Our main loop just calls a routine called check clock buttons. And here's that routine. I'm not going to go into detail here as it's really not in the scope of this article. Basically, all it does is clean up the switch press so that there is no contact bounce and sends a nice clean pulse to the 6502. It's not long, and you can have a look later at your leisure if you wish. Code available on the website. So, we'll go on to the meat of today's episode. What does the 6502 do when it starts up? The datasheet is our friend here. Bring that up for you. The reset or not RES pin is the pin that resets the processor. Before a reset will start it, it needs to be held low for at least 2 clock cycles. I'm sure you can read this as well. Then pulled high again. At this point, our processor wants to start executing code. But where from? You might want your code to execute from, say, hex 1000. Another designer might want it to execute from hex 6000. How can you tell the processor where your code starts? The 6502 has some memory locations reserved for what are termed vectors. A vector, in computing terms, is an address in memory that stores another address. Sound confusing? Well, at first hearing it can be. Let's use the magic of computer-aided animation to explain. Well, here we are in the magic land of animated explanations. I'm going too far with this, aren't I? Well, nevertheless, here we are. So here's our 6502, and we have some memory, but more specifically, we have a particular part of memory. In fact, it's the very top of the 64K address space that our 6502 can access. There is nothing higher than these addresses. At the very top, we have 3 vectors, one each for IRQ, interrupt request, NMI, non-masked interrupt, and right in the middle of that sandwich, we have our reset vector, RES. In these memory locations, it is up to you, the hardware/firmware designers, to store the address that the processor should use whenever one of these events occur. So for us, when we hold the reset pin low, then high, the processor will stop what it was doing and go and fetch the address that you stored at the reset vector. It will then start running the code at that address. So using our earlier example, we could store 1000 hex there, and the processor will start running code from hex 1000. So you would always have some ROM at the top of your 6502's address space. Other processors, they do it differently and have their vectors at the bottom or start of memory. This may seem to make more sense, but there is a good reason 6502 does it this way, and it's all to do with a special place called zero page. But more on that in a later episode. You will notice that we need 2 bytes for each address vector, and that is because the 6502 uses 16-bit addresses to address the total of 64K of memory. So 2 bytes are needed, one for the lower byte of the address and one for the high or upper part of the address. On the 6502, the lower byte comes first, stored in FFFC, followed by the high byte in FFFD. This is arbitrary. Other systems do it differently with the high byte first, followed by the low byte. It's completely arbitrary, just up to the chip designers which way around they will access those addresses. So if we wanted our program to start at 1000 hex, our processor to start running code at 1000 hex on PowerUp, we will put 00 into FFFC and 10 hex into FFFD. You can now see what the reset sequence does. It sends out FFFC on the address bus, and the data of 00 will come back on the data bus. The 6502 puts this to one side internally for now, just keeps hold of it, saves it, nice place, it's there, it's saved. And then it then sends out the address FFFD and gets 10 hex back on the data bus. It then puts these 2 together into a special register. Now a register is just some internal memory on the processor. And in this instance, this particular register has a special name and it's called the program counter. It is the program counter's value that is then put onto the address bus to go and fetch the first instruction of your code from, in this example, 1000 hex. Phew, so that's vectors and the reset sequence. Let's see if our processor is doing that. First thing is, how would we know what it's doing? We need to be able to see what is on the address bus. To do this, we could attach some LEDs. Now, a word of caution. The 6502 buses are not designed to drive any real load. LEDs all connected to it could damage it. Particularly if you're using an old 6502 rather than like a new one that I'm using, the W65CO2. WDC65CO2 from Western Digital. So to try and minimise the current flowing through the processor, I've used an almost massive for this task 10K resistors, or I will be doing. This still provides plenty of illumination to see the bus, and I'm also going to connect up only the lower, which is going to be these first 8 here, only the lower 8 bits of the bus, as this is enough to see if our processor is doing what it should. If you remember, the address put on the address bus is FFFC, then FFFD. The high byte remains the same, FF. It's only the lower byte that changes. Seeing these values on the address bus, lower byte, we should be enough to determine if we've got a boot-in 6502. So, by the illusion of filmmaking, here we have the completed board. Here's the circuit diagram as well. You can see the 10Ks in series with the LEDs. And also you can see we've added a connection from the Arduino to the 6502 reset pin. It's this white wire here, and it's going around to the reset pin there. We'll need to manipulate this, obviously, too, to get it to start its reset sequence. We've also got an LED hooked up to the reset pin so we can see its value. We'll need to flip my board around in a second, as the Arduino bit A0 is at the right hand side here. So A0 is here on the 6502. It's obviously for easiness of wiring, I've just gone straight down like that, with all of them going down to A7 here. So that's the complete opposite of number systems. In other words, the lowest significant bit is at the left on this, and the most significant is on the right, whereas number systems, it's the least significant bit on the left going up to the right. So for example, units are at this side in the tens system, in decimal, then in tens and the hundreds, etc. So in binary, we want the least significant, the A0 bit, at this side. So we'll have to flip it physically around so that it actually makes sense. So we'll have to do that. So now we've got A0 here going up to A7, and that will make more sense as we go on. Let's look at the new Arduino code to handle this reset. We've added a new define here that states that we're connecting to pin 2 of the Arduino, and that's our reset line. That's that white wire that then connects to the 6502's RES pin, reset pin. And then in the setup, we've added this line where we reset the 6502. Going down to here to where the function is, we can see we've got a clock speed. We just set as a, it's like a constant basically. And it's set to 1 millisecond, just as an arbitrary value really. It's obviously a very slow clock for the 6502, but it'll do for our reset. If you remember, the reset line needs to be held low for at least 2 clock cycles, and that's what we're doing here. So we're putting it low, and then with this various ups and downs of the clock, we're doing 2 complete clock cycles. And then we're finally bringing it back high again. At that point, our 6502 should now be ready to start its reset sequence malarkey. Job done. So let's power up. And if you look, I'm pinching 5 volt power from the Arduino itself here. 5 volts coming out on that pin, and we've got the ground there, and that supplies all these power rails and therefore the 6502 itself, LEDs, etc. The LEDs are generally, they're all lit up at the moment. Usually they can light up in a different pattern than this. They are currently random. The documentation says it will take 7 clock cycles to get the address you want the processor to start at from the vector locations FFFC and FFFD, low and high byte, if you remember. These LEDs will show the binary pattern for FC first. This is the location of our low byte for our address to start at. But what is that pattern? Well, because I'm so generous and everything, here it is. I've actually done FC and FD. So we're expecting the first 6 LEDs to be lit up and the last 2 to be off for FC. Then the next address we should see would be FD to get the high byte of your starting address for your code, and that should be the first 6 again, LEDs lit up. Then this one should be off and this one should be on. So we're going to look out for those bit patterns. If you'd like help converting from hex to binary to decimal, etc., then see the link in the description below where I go into some detail on converting number systems. I think that was a previous episode, possibly one before that. Either way, let's press our clock down first. So it has actually done the startup sequence that we saw in the code where it held the reset low and then high. That's all been done. You can see the reset, this blue LED is lit up and we're ready to roll. So we'll press our clock down and then back up, and that's 1 clock cycle. So that's clock cycle number 1. Let's carry on and watch out for our bit pattern, and which is going to be this one we're looking for first, FC. So we've done 1 clock cycle. So 2, 3, 4, 5. Okay, you're not there yet. You can see some randomness. 6. We seem to be seeing that one. Remember, it's 7 clock cycles, and then we should have got the address, and we're on 6 already. Do another one. 7. Now we've got this, but we're already on clock cycle number 7, and the reset sequence should be finished, but we know it hasn't because it's only got the address FC. Let's see if it puts out FD on the address bus next. So this one should light up, and it does. So that was clock cycle. That was 8 clock cycles. Something's amiss. The data sheet, which I'll bring up on screen now again, says it should take 7 cycles and it's got your address all stored in the process, all done and dusted, and yet this took 8. What's happening? Is the datasheet wrong? Well, looking at it again on the datasheet, it states that the reset pin should be brought low for at least 2 clock cycles. And I'll get my code up on screen again as well. Okay, we're definitely doing that within this code. Doesn't mention anything about what the speed should be. We're doing 2 full clock cycles. So what gives? Well, it turns out, after some investigation where I had my head scratching for a while, when I first did this, it turns out that the speed of the clock matters. The slowest delay I can have here without having no delay is 1 millisecond. And that's what it's set to. We could let the code rip as fast as it can, but I wanted a bit more control than that, which is why I've got that. And the datasheet doesn't say anything about the speed of the clock. And remember, these modern 6502s can run at no speed. You can hold them indefinitely with the clock stopped for as long as you want. So let's look what happens if I don't even bother generating a clock whilst it's resetting. I'll just rip out this code here, we'll recompile and upload. Okay, so we're ready to go. We've done a reset. The reset pin is high. Let's investigate what happens now. Let's count our clocks again. So if you look, they're all off at the moment as well. As I said, it's very random. So 1, 2, 3. Ooh, got that clock, that pattern. 4, but then random again. So I don't know, we're not expecting anything. Well, at least 6, 5, clock cycle 6. And yes, we've got FC. We have got that. The next one we're looking for is FD. So we're just expecting this one to go on. This is going to be clock cycle 7. And there we go. Clock cycle 7. We have had clock cycle 6 was that. Clock cycle 7 was that. We have loaded that address in. Everything fits with the data sheet. It works perfect. So the 6502 does not need a clock input when activating the reset pin. In fact, it seems to affect the processor if you give it one and cause it to be out of spec, not correct with the data sheet. And obviously out of spec here would mean very little. Now I can't find it saying this in the documentation that the clock would affect it this way or anywhere else on the internet, admittedly after just a cursory look. So this is my theory. The reset circuitry inside the 6502 is clock independent for the initial part when you're pulling the reset pin low and then putting it back high. It just does its thing at whatever speed the circuitry can run at. Once that initial part is complete, from that point on, it's ready. If it gets clock signals between the reset pin being low and going high, it seems to confuse it a little. Not a lot, just a little. Enough to extend the reset sequence by 1 clock cycle for some reason. At least that's a behaviour I've been able to replicate over and over again. Weird, but there you go. So's life. If anyone knows if this behaviour has been found before, then please leave it in the comments. It'd be kind of nice to be the first to document this, but with the size of the internet and the age of this processor, I doubt I am the first. And I wonder if this behaviour has been right there from the start, or just in these more modern versions. So let's go back to the code that drives the processor correctly. One thing I've also added here is a line that sets the reset pin to an input and pulls it high. The reason for this is that the Arduino's default state for an output pin is low, which is not what we want the reset pin on power up to be. We want it high. So by adding this line and then setting it to an output means it will start off as an output already high. By the way as well, before anyone comments, I did retest this weirdness I've been talking about with this line in and it made no difference. All uploaded, let's go through it one more time to summarise. So I'm just going to press the Arduino's reset button here. So it's reset, blue light's gone high. So at power up, the processor has had its reset line held low for 1 millisecond and then brought high. We've sent no clock pulses in between it doing that. And it's shown that it's high by this blue LED here. We then give the processor a clock pulse by pressing this button down, and down sends the clock low, and we can see that the clock's gone low, and back up brings it high again. That's one full clock cycle. On clock pulse 6, so that was 1, so 2, 3, 4, and ignore all the randomness, totally unimportant, 5, 6, we should see the address FFFC, or in this case we're just looking at the low byte, so we're seeing FC here on the address bus, as the 6502 gets the low byte of your code where it wants to start from. On the next pulse, so that clock pulse, this is number 7, it should get the high byte at FFFD. And as mentioned, we're only showing the low byte of the address bus for simplicity, as it's the only part that changes. So counting 1, 2, 3, 4, 5, lots of random patterns on the 652 address bus as it does its stuff. Then on 6 you should have FC, and on pulse 7, FD. And we did. Fantastic. So there it is. The 16-bit address where we want the processor to start XR code is now loaded into the program counter, and we're ready to go. Of course, this address is just garbage, as we've got nothing attached to the address bus or data bus. There's no memory here or anything. So we're just farting in the wind here. In the next episode, we'll attach a ROM onto our address bus and program those vectors correctly to execute some code of our own. We'll also attach my more advanced Arduino debugger using an Arduino Mega, which was designed and built nearly a year ago now. You can tell how long I've been working on this project. And this will help us examine the data buses with far more detail. So, the usual, please like and subscribe if you feel I deserve it. Ways to support the channel are in the descriptions as usual below. And thanks to my patrons. And thank you all for watching. Till next time.